Thank you. It's a pleasure to be here. So let me sort of start right off the bat by writing down the André-Oort conjecture. And then as the talk progresses, we'll move more and more into Colmez territory. So this conjecture deals with a Shimura variety, S. So actually, last time I gave this talk, somebody asked me what I mean by this. And I mean sort of an actual variety, not like an inverse limit of level things. So an actual Shimura variety, like the modular curve or something. And V in S, an irreducible subvariety. And suppose that V has the Zariski dense set of CM points, so of special points. So if we intersect V with the CM points in S, and we take the Zariski closure, then we get V back. And the conjecture is that this implies that V is a special subvariety. Or maybe sometimes it's written down as a Shimura subvariety. Okay. This is the conjecture. It sort of is very clean, just classifying Shimura subvarieties by containing these points. So there's been sort of a lot of work on this conjecture in recent years. So I'll just mention a couple of partial results. So there's a theorem by Klingler, Olmo, and Yafeev. They sort of came out with it in 2006, and then I think it was finally published in 2011 or so. So at some point between there, it became a theorem.
You think when it's published, it changes that?
Well, I don't. No, I said somewhere in the middle. I don't really know. And that the generalized Riemann hypothesis implies the André-Oort conjecture, sort of in general. And specifically, they needed the Riemann hypothesis for Dedekind zeta functions of, sorry, I keep hitting this chair. Dedekind zeta functions of CM fields. So a little bit later, I'll give a brief sketch of why Riemann might be useful. But right now, let me leave it at that. And then there was a big breakthrough by, I should also mention here Edik Soven's name. He wasn't on the sort of final paper, but he had somehow the initial idea for the whole project. And so there was a theorem by Pila in 2011, which in the case where S is just a product of modular curves, if S equals this, then André-Oort is true unconditionally. So he brought in sort of a lot of new tools, and he had somehow a general program to prove André-Oort, which in theory could work in general, and he carried it out in this special case of x1 to the n. And so one of the ingredients that came up in his work is a conjecture which I think is of independent interest. And you can somehow conjecture. And so somehow, glibly, I'm going to call it conjecture 1 sub g. And you'll see why in a moment. And what it basically says is that Galois orbits of CM points are large. Okay, so if you take a CM point, it can't be defined over a low-degree number field. So there's a conjecture you can make for any Shimura variety. Let me somehow keep things relatively simple by only saying what it is for AG, which will be the subject of my talk in any case. So let AG be the Shimura variety, which is the moduli space of principally polarized abelian varieties of dimension G. And now suppose that x is a point in AG, such that if you look at the corresponding abelian variety A sub x, then this has CM type corresponding to some CM field K with some CM type phi. And I'm only going to state sort of the simplest case, which is that the degree of K over Q is 2G. Phi is a simple CM type. And in fact, the endomorphism ring of this guy is the full ring of integers of K. It's somehow the basic case that one looks at. Then the conjecture is that if you look at the Galois orbit of this point x, let me write it as the degree of the field definition of x over Q grows at least as fast as some constant times the discriminant of K to the power of some positive number that depends only on G. OK? So some quantified version of saying that Galois orbits are large. In fact, you can state sort of an easier conjecture, or theoretically an easier conjecture, where you just sort of say finitely many of these are defined over Q, for example, or something like this. And in all the approaches I know, somehow, they're the same difficulty. So if you can prove anything at all, you'll probably prove something like this. At least that's what experience somehow shows. And so then it's a theorem, sort of as a result of a lot of work in the past sort of 5 years, or maybe 4 years. So it's due to Pila and myself in the case of AG, and then Klingler, Ulmo, and Yafaev, together with some recent work of Christopher Daw and Martin Orr for a general Shimura variety. And what this theorem says, I only state it in the case of AG again, because I didn't state this conjecture in general. But if you assume conjecture 1R for R less than or equal to G, then you get André-Oort for AG. And if you assume somehow the corresponding conjecture for general Shimura varieties, then you get André-Oort for a general Shimura variety. All right? So somehow I'm not going to say any more about André-Oort. From now on, I'll be focused entirely on this somehow independent conjecture. So what was known sort of so far, the most sort of general version, there'd been some also similar work by Ulmo and Yafaev. And then I proved in my thesis that so conjecture 1G is true for G at most 6. Somehow there's some trickery you can play, and then it just stops working after a while. So today I want to announce sort of recent work with a little t, because it's still based on some work in progress, that 1G is true for all G. So as a result, you get André-Oort for AG. So let me sort of mention that it's sort of natural, given this, to try and do the same thing for a general Shimura variety. But it seems very unclear how to generalize the approach to a general Shimura variety. So maybe it's possible, but the experts I've talked to seem to have sort of a lot of skepticism. So before I move on and just somehow talk about this problem and explain what it's really about, let me just give you a brief sketch, a very informal sketch of why this conjecture could possibly be useful to prove something like André-Oort, why you might care. So just like a 2-minute thing. So suppose that you have a subvariety V, say in AG, which is a, for which André-Oort fails. Suppose you have something like this. So then V is defined over Q bar, because there's the Zariski closure of a bunch of Q bar points. So V is defined over some finite number field. And I'm going to cheat and say that rho log V is defined over Q, which you can sort of make happen anyways by taking a finite union of conjugates. And so then the observation is just that if X is a CM point which is in V, then the entire Galois orbit of X is also inside V. That's because that's how algebraic variety works. And so the point is, if you sort of start working on André-Oort, you might have this very, very sparse set of CM points sort of independently, and it's hard to make them work together. Whereas if you know this Galois orbit is large, then all of a sudden you have sort of a substantial amount of CM points that look very similar, and they're all in this variety. And so there's sort of a lot of approaches you can then take, starting from this fact. And in fact, that's also the approach that Klinger-Umoyafev took, and somehow every approach uses this somehow basic step. All right. OK, so let me now talk about this conjecture 1G. So let me sort of mention first what happens in the case of elliptic curves, and then I'll sketch what happens for CM abelian varieties. So suppose E is an elliptic curve, and the endomorphism ring of E is the full ring of integers inside some imaginary quadratic field, K. So E is a CM elliptic curve. So then one has the following theorem. So you can call this the theorem of complex multiplication, at least one of its incarnations. And it says the following thing, that first of all, if you look at the J invariant of E, and you add it to K, then you get something which is Galois over K, which a priori is not clear. And moreover, this group is isomorphic to the class group of K. OK, so somehow this Galois orbit in this one-dimensional case has this somehow very classical interpretation. This is an object that people know and love. And then you have the very useful theorem of Brouwer and Siegel. I think in this case it's only due to Siegel. But no matter what I write, I get corrected. So I'm just OK. Well, I was going to just close the bracket, but OK. So Brouwer and Siegel, which tells you that the size of this class group in the imaginary quadratic case, so that nothing like a regulator gets in the way, is roughly the size of square root of the discriminant. So I'll write it as the discriminant to the power of 1/2 plus little of 1, some number that goes to 0.
However, you only need a small power. Then that was known by Landau.
Right. Right. That's true. That's true. Yeah, so right. So in fact, we don't need this equality. All we need is that this number is pretty big. And that was already known to Landau, and then Siegel somehow made it much stronger. So maybe in this case, it's not Brouwer. But I think next time I write it, it'll be Brouwer. OK. So Brouwer says this. And so as a corollary, I'm not going to claim this for myself, though it's not been written down anywhere. But if you just add these two, then you get that the degree of the J invariant of E over Q, the size of this degree, is of size discriminant of K to the 1/2 plus little of 1. So K is degree 2 over Q. So somehow these two numbers are off by at most a factor of 2. OK? And so that proves conjecture 1 sub 1, in fact, with sort of plenty of room to spare. All right. So that's the elliptic curve case. So now why do things get messier when you bring in higher dimensional abelian varieties, higher dimension than 1? So now let's let A be sort of a CM abelian variety. And like before, the endomorphism ring of A we're going to assume is just the maximal ring of integers of some K. And the CM type of A is phi. Just got some CM type phi. OK, so then we still have a theorem of complex multiplication in this case, but now it's a little bit more complicated. So now we have something called the Shimura Reciprocity Map. And what it does is the following. You let K star be the reflex field associated to K together with its CM type. So it actually depends on this as well. But it's some other CM field. It's not really a scary object by itself. And then you have this canonical map. I'm going to call it R sub K phi from the class group of K star to the class group of K. Something you can write down combinatorially just in terms of the Galois theoretic data. And so then the theorem in this case, this is again the theorem. It's called the theorem of convex multiplication. One incarnation of it is that, so I'm gonna mess this up if someone wants to correct me. But last I checked, what you do is you look at the field definition of A adjoined K, and this will contain K star, in fact. And then if you look at this Galois group, then this is isomorphic to the image of R sub, what did I call it, K phi. All right? I'm not entirely sure if it's a K star or a K here, but for my purposes, I don't really care, because I only care about the size of this number. But I think this is right. OK? All right, so why is this harder? Well, now to show that this number is big, which is really all we care about, that the size of this group is big, all we need to show is the size of the image of this map is big. And Brouwer and Siegel tell us how big both of these guys are. But the problem is that understanding images between class groups is much harder than understanding sizes of class groups on their own. And let me explain why. But first, let me just point out that in the G equals 1 case, K star turns out to equal K. And this map, as you might have guessed, is just the identity map. So in this case, the image is the whole thing, which is why it was so much easier in the case of G equals 1. So let me erase this. And let me explain somehow the fundamental difficulty that comes up in this images between class groups problem. And so here's sort of a hypothetical example, which you can imagine showing up there, is that the reciprocity map, so in this example, K equals K star. And the reciprocity map is just the multiplication by M map from the class group of K to itself. Somehow it's, this is in some sense the simplest you could hope for it to be. So in this case, the size of the image, well, of the multiplication by M map is, using group theory, the size of the entire class group divided by the size of the M torsion in the class group. And it turns out that bounding M torsion in class groups is extremely difficult. So this is a problem about which we know sort of almost absolutely nothing. Only in extremely low degree cases can we provide somehow some sort of non-trivial bounds. So to illustrate just how little we know about this problem, which I think is very interesting, there's a conjecture of Shouwu Zheng. It's sort of a folklore conjecture, but he wrote it down, which says the following. I think it was 2006, right? 2006? Oh, OK. Well, then, I can write anything I want. 2004, which says the following. So fix M and N, and let K just be a field of degree N over Q. Then if you look at the size of the M torsion in K, then this grows subpolynomially in the discriminant of K. OK? So we somehow expect very, very little torsion. And so by the Brouwer-Siegel theorem, this is certainly at most the size of square root of a discriminant, because this is the size of the entire class group. OK, so it's somehow extremely open to get, I guess you could call it a subconvex bound in this case, to just put 1/2 minus a tiny amount here. Only in the case, I think, where sort of m is 2 and n is at most 4, or m is 3 and n is 2, can we provide any bounds whatsoever? Otherwise, it's completely open. All right? But so if you could resolve this difficulty, if you could prove Zhang's conjecture, or even much less than Zhang's conjecture, somehow some non-trivial saving, then you could resolve this conjecture quite easily. It turns out that that's the main obstruction to understanding this. OK, but we can't. So that's why this is hard. All right, so now let me talk about the conjecture of Colmez and how it plays a role. So let me say a few words about Faltings height. So this was invented by Faltings in order to prove his big theorem, the Mordell conjecture, one of his big theorems. And what it is a measure of arithmetic complexity to abelian varieties that are defined over the algebraic numbers. So suppose that A over Q bar is some abelian variety. OK? And so let K be a big enough field such that A over K has action. And I want to arrange it that you have sort of a Néron top form. I'm going to call it omega sub A, I guess. So it's a form over the integral model for A, somehow that generates all the other ones. And so then you define the Faltings height of A to be the following. We're going to include a 1 over the degree of K factor to make this definition independent of K. And now we're going to sum over all embeddings of K into the complex numbers of the log of the integral over the complex points of A embedded via sigma of omega wedge omega bar. OK, so if A, say, is defined over Q and has a good reduction everywhere, we find a Néron differential, and we integrate it and take log. Somehow it's the size of the volume of A. All right? OK, so it should not be immediately clear this has any properties whatsoever. But in fact, it turns out to be a very good function. It behaves like a height function should. So if you fix the field K, there's finitely many abelian varieties under a given height. And if you take a height on the moduli space, it's very similar to the Faltings height. So somehow, it's a very good canonical height function you can define in the abelian varieties. All right, so because it's a precise height function and not just something defined up to a constant like V heights usually are, you can hope there are some nice formulas to go around. And so there's a beautiful conjecture due to Colmez, which says the following thing, that suppose A has CM type K phi, and the endomorphisms of A are the full ring of integers. He actually insists on this in this case. I presume you can get a formula in any way, but in any case, but his formula, his conjecture is written down, has this condition inside it. Then the Faltings height of A is equal to the following thing. You take a sum over irreducible representations rho from the Galois group of the normal closure of K over Q to some GONC. So you sum over all irreducible Artin representations. And now you have some rational constants, 0 phi, which depend only on the combinatorial data involved, not on the actual field, just somehow the group G together with combinatorial data of phi, multiplied by the logarithmic derivative of the L function at 1 plus the log of the Artin conductor of rho. Just to GONC is what I wrote. This is K nor, the normal closure of K. Because K might not be Galois, so I'm just taking, just the normal closure over Q. That's right. OK, so we're, it's not really relevant to us, but these are numbers that are rational and somehow only depend on combinatorial data. OK, so this is a beautiful conjecture. And let me write down a sort of immediate corollary of it once you know what modern analytic number theory already knows. And the corollary is that if you look at the Faltings height of this abelian variety, I'll write it in absolute value, but in fact, Faltings height can't get too small, then this grows subpolynomially in the discriminant. So it's kind of funny. It's a very beautiful and precise formula. And we're only going to use it in this very sort of perverse, lighthearted way. But if without this formula, I'm hard pressed to give you any bound whatsoever on this Faltings height. So I used to say that I in fact, can't give any bound on it. In fact, I've thought about it. You can probably give some exponential bound to discriminant if you work really hard. But if you want to give a reasonable bound for this quantity, I really can't see how to do it without using some precise statement like this. So it's kind of a funny situation, I think. So let me give the proof. I'll give it inside of this box. OK, so because these guys only depend on combinatorics, there's finitely many possibilities of them. So if I just show you that all of these terms are small, then that'll show that their sum is small as well. And the proof is the following. So let's see. Well, the Artin conductor is bounded by some power of the discriminant of K. And log grows subpolynomially. So that's this term here. Proof. We need to bound this from above and this from below. So L of 1 rho, this is actually the most subtle term in this expression, in absolute value, bounded below by the discriminant to the little of 1. So I'm going to get it wrong again. I think it's just Siegel who did this, right? Or is this Brouwer now?
Brouwer.
OK. Brouwer Siegel. That's somehow what their main theorem about class groups amounts to, is this lower bound. So it's deep. It's been known for a while, but it is somewhat deep.
This is the source of every ineffectivity as a whole. Even your solution of André-Oort.
Right. Absolutely.
There is one part that there's a lot of debate with people.
There are certainly several cases you can prove effectively from Stark's theorem, from Stark's work.
No. I'm talking about the whole
Oh, I see.
which is used heavily.
Right.
It's under the rug here.
Right.
That's effective, and I
Right.
think that it will be effective. Even
Oh.
if it doesn't
I see. OK. And so finally, you got to bound L1 prime rho. And this is true, that this guy small is true by the standard convexity bound. Let me write it this way. The standard convexity bound tells you that L is small near the 1 line. And then if you combine it with Cauchy's integral formula, you get it for the derivative as well. Pardon me?
The G and N are.
Yes. So yes. Yes, everywhere here G is fixed. Absolutely. Throughout everything I do. Yeah, if you start varying the degree of the number field, it's a whole different ball game, which I know nothing about. So G is always fixed. OK, but you put these three facts together, and you get immediately from Colmez. And somehow some known but deep work. All right, so Colmez is not known, and it doesn't seem like it's very close to being known. But there's somehow an average version of it which is known that turns out to be sufficient, which is why we can still end up proving the theorem. But I want to save that to the end. And right now, let me just show how Colmez would imply the André-Oort conjecture. I want to give you a brief sketch of somehow the ideas behind the proof. So theorem, the Colmez conjecture implies André-Oort. Well, let me say it implies conjecture 1G. That's what I'm really going to prove. OK? So I want to explain how that goes. So it's going to be a few ingredients. One ingredient is going to be this corollary here. Another somehow massive ingredient we're going to use is the theorem of Masser and Wuttholz. And the version I'm going to use, I think, was proven in '96, though they had worked on it for several years on refinements of it. And this is going to be a huge powerhouse theorem. They proved it to give a different proof than Faltings of the Mordell conjecture. Of part of the one. Really? Oh, part of. OK. Part of the Mordell conjecture. OK. And it says the following. So suppose that A and B. So once again, let's fix G. Always fixed. And suppose A and B are abelian varieties over some number field K of dimension G. And say that somehow I know that they're isogynous. So now there exists some magical isogeny between them. So then it turns out that there's in fact an isogeny between them that's not too big. It has a degree that's not very big. So then if you let n be the minimal degree of an isogeny between A and B, then n is bounded above by the maximum of the Faltings height of A, or I could put B here also, and the degree of the field K over Q to the power of some constant, let me call it C sub G, depending only on G. OK. So if I give you two abelian varieties that are not arithmetically complex, defined over some low degree number field, and you know that they're isogynous, there's in fact a low degree isogeny between them. All right? OK, and it turns out that these two are sufficient to prove conjecture 1G. So let me now give you the proof of 1G from these two guys. And we'll do it as follows. So define a set S to be the set of all abelian varieties A, such that A is principally polarized, the endomorphism ring of A is the full ring of integers of K, and A has CM type K, comma, some phi. OK? So look at all such abelian varieties. Now, in the case of elliptic curves, these form a single Galois orbit. In general, that's very much not true. They can split up into lots of Galois orbits. And even though the size of the Galois orbits we're trying to get at, and that's kind of subtle, the size of S is actually pretty straightforward. So this is up to constants. Let me put it in quotes. I'm not quite sure what the constants are. But the size of this is the size of the class group of K divided by the size of the class group of the totally real subfield of K. And again, using Brouwer-Siegel, that happens everywhere. This is at least of size discriminant to the 1/4. Okay, so regardless of what's what, if you give me a CM type, then I can give you lots of abelian varieties that are principally polarized of that CM type. Sort of, they exist without much fuss. Okay, and let me move over here. So if A and B are in S, then A and B are isogynous. That's true just because they have the same CM type. All abelian varieties of the same CM type are isogynous. And the field by CM theory of definition, let's call it H sub k of A in S, is independent of A. So they're all defined over the same field. That's not too important actually, but it's good to keep in mind. All right, so now all these guys are isogynous, and there's a ton of them. And an abelian variety does not have so many isogenies of a given degree. Only has polynomially many isogenies of degree n. So in fact, what you can do is you can find A, B in S with the minimal degree isogeny, at least, I think it's like the discriminant of k to the 1/4g. The power of some number. It doesn't really matter what that number is. So there's two guys that are pretty far apart just by virtue of there being so many of them. So then if we apply Master-Wustholz, we get that this number, which is at least the size of the minimal degree isogeny, is bounded from above by the max of the Faltings height of A and the degree of H sub k to the power of this magical constant C sub g. Okay? And now Colmez tells us that this guy can't be responsible, because this guy grows subpolynomially. And so we conclude that this guy is big. As a result, this degree is at least of size the discriminant to the power of 1/4g times cg. A little bit. Any power. Yeah. You can actually make it not so bad. So you can actually make this just a quarter if you're a little kid. CG is not so bad now either. It's within a constant of what it should be. It's roughly 2 times g or something. That's much since Master and Wustholz have improved it. But the problem is, see, morally speaking, you can't get a good enough constant here. And the point is that you have lots of different CM types. And for different CM types, the Galois orbit's actually of different sizes. So you can at most get the size of the worst orbit. And if you're dealing with the best one, it's nowhere near good enough. So in principle, this approach, until it can distinguish between CM types, can't really give you good constants, just constants. All right, so that's the end of this proof. So now, maybe I should, well, yeah, let me go over here. All right, so that's how you would do it. Unfortunately, we don't have all of Colmez, but there's work in progress by, I'm going to misspell some names now. So I apologize for that. André-Oort, Goran. I messed up already? Sorry? Oh, there's one. The I is an A. André-Oort. I see. Thank you. André-Oort, Goran, Howard, and I'm going to screw up even worse now. Metapace, is that right? No. Pera? I can't even. Let me write MP. MP. I apologize. I'll apologize to him in person next time. All right, but his contribution is not smaller because his name is abbreviated. So Kirti, I know his first name. All right, so these four gentlemen have this theorem in the case where you fix k, but you average over all CM types phi. So they have the following theorem, which is that if you sum over phi the Faltings height of an abelian variety with CM type k phi, what you get is the sum, well, the sum over all phi of the sum over all rho of somehow what's supposed to go in there, the same thing as you see over there. So they don't quite have this theorem. They're a little bit off. So they get the following theorem, plus at primes dividing twice the log of the discriminant, sorry, twice the discriminant, I apologize. Primes dividing twice the discriminant, they're off by rational multiples of log p. Okay, and so they can now show that they aren't off by too much. So each of these numbers is bounded by some absolute constant depending on g. Okay, so they would obviously want to just have this theorem, the average version, but somehow they can't handle some intersection theory at some bad fibers, which is why they're off by these quantities, but they can control how much they're off by. All right, so they have this averaged version. And then it's a fairly old theorem of Bost that if you take any abelian variety A over Q bar of dimension G, then the Faltings height of A is actually bounded from below by some constant depending only on G. So some, let me call it capital A sub G. No, let me call it, I don't know, delta prime sub G, whatever. This is a negative constant, by the way, so it's not always positive, but it's still bounded below. Okay. But so as a consequence, you still derive this corollary just the same, because you get an upper bound for the sum. Each term is bounded below, so each term has to be bounded above as well. All right. OK, well, that's all I had to say. So maybe I'll just stop here. Thanks.